Guys, for today's cyber lesson, I thought I would walk you guys through an example problem where we solve to find the speed of a roller coaster at various points along the track using work and energy. As we've done before, we've solved similar kinds of problems with our kinematic equations, but in this case, because we get a curved track, you get a changing acceleration as opposed to one when you get a flat track at various angles where we can use that A prime equation. So this is a perfect example where work and energy come into play. Now, what's important in this problem, we have a roller coaster going to different points on the track. The problem is looking to calculate the speeds at points 2, 3, and 4. And they tell us to assume no friction. And when there's no friction, we're not losing energy to heat. And so our total mechanical energy is conserved at each point. And mechanical energy, we can call that ME, is just equal to any kinetic energy we have from motion. If we have speed, we have kinetic energy, plus any potential energy we're going to have at any point. And as we've talked about before, we've defined what kinetic energy is. That's just equal to 1/2 the mass times the velocity squared. And the only type of potential energy we've discussed so far has been gravitational potential energy, GPE, which is simply a function of the mass, gravity, and the height you are above whatever arbitrary 0 point you have in the problem. And because energy is conserved in the case where we have no friction, the energy before the initial energy is equal to the final energy. So if we can figure out what energy we have at each point, that amount of total energy in joules will be constant throughout the problem, which is what we use to solve the problem. So let's look at this example now. We have a roller coaster. It's got various heights. I'm just going to fill in the values. H1 in my example is 50 meters. H2 is 16 meters. And the third height is 23 meters. So like most roller coasters, all the work is done at the start by a motor that pulls it up to the highest point. Usually you have a big drop to start the roller coaster ride. And what you're doing is work is being done to change your gravitational potential energy, to give the rider energy at the top of that ramp, and then gravity takes over. And as you lose gravitational potential energy going down the track, you're gaining kinetic energy. At the lowest point, you're going the fastest, and then that speed is transferred back to gravitational potential up to point 3, and then back into more velocity at 4. And usually you finish the ride at the bottom. And that's how most roller coasters work. They take advantage of this transfer of energy. And so what we really need to figure out, we want to find the speeds at points 2, 3, and 4. But we need to know how much energy we have to work with. So like any problem with energy and gravitational potential energy, we want to identify where our 0 GPE is located. And so we're going to look at our track, and I'm going to call point 2, where they're measuring the height from, as our GPE equal to 0. And what's convenient about that is we know that when we get to point 2, we will have 0 gravitational potential energy, so that all of our energy at this point is KE. It's all kinetic energy. And at the top, where it says we're leaving from rest, this is all GPE. And at points 3 and 4, you're going to have a combination of whatever GPE we have at 3 plus whatever kinetic energy we have at point 3. And at point 4, we're going to have any GPE at 4 plus any KE at 4. And again, because there's no friction, the total amount of energy in joules is going to be the same at each location. So the energy at 1 is going to be equal to the energy at 2, which is equal to the energy at 3, which is equal to the energy at 4. And so we're going to use that fact to solve and figure out the speeds, or the velocities, at each location. So let's figure out what our energy is at 1. At 1, we're at rest, so we have no kinetic energy. It's all GPE. And our equation is the mass times gravity times height. And at this point, we know for point 1, this is going to be the mass of the roller coaster times 9.8 times the height of 1, which is going to be 50 meters. Now, they didn't give us the mass. If we had the mass, I could figure out that exact amount, but I don't know it right now, so I'm just going to keep that value as m, and I can use my calculator, do 9.8 times 50, and I'm going to get a value of 490 times the mass, and that's going to be in joules. So if I knew the mass, I'd know that amount. What really matters, though, is in order to calculate the speed at point 2, we know that the energy at point 1 equals the energy at point 2. The energy at point 1 is just the GPE at 1 plus the kinetic energy, which is 0. And at point 2, we have 0 GPE because we're at the bottom, so we're all KE at point 2. And so I can plug in, I just calculated what the GPE at 1 is. That's 490 times the mass. And the kinetic energy at 2 is going to be our equation for kinetic energy, 1/2 the mass, the velocity at 2 squared. And there's my equation. You notice they didn't give us the mass, but the mass is going to cancel on both sides, and we can solve for the velocity in this equation. I'm going to multiply both sides by 2 and take the square root, and I get my velocity at point 2. When I take 490, multiply it by 2 to get rid of the half, and take the square root of that value, and I get 31.3 meters per second. So that's our velocity at the bottom of the ramp. That's going to be the fastest this ride is going to go, because that's the lowest point of the ride where all the energy has been converted to kinetic energy. So now we're going to move on to point 3. They want to know the speed at point 3. At point 3 on the ride, that total amount of energy that we started with at E1 has got to be equal to the energy at 3. So again, the energy at 1 was 490 times the mass. The energy at 3 is going to be a combination of the GPE at 3 plus the kinetic energy at 3. And that's going to be the mass of the ride times the gravity times the height of 3 plus 1/2 the mass times the velocity of 3 squared. And again, it's 490 on the left side. And if you notice, all three terms have m in it, so I can just cancel out the m's. The mass doesn't matter in this ride, which is why we can take the same ride with any number of passengers, because you can put more people in and it should still work as long as you can get the ride to the top of the hill. I'm going to plug in the values I know, so I've got 490 on the left side right now. 9.8 is g. My height of 3, they tell us, is 23 meters. Plus 1/2 v3 squared. So yet again, I have one variable that's unknown. 9.8 times 23 is 225.4. 490 equals 225.4 plus 1/2 v3 squared. I can subtract to isolate the v3 squared part. So I've got 490 minus 125.4. I get 264.6 is now on the left side. And that equals 1/2 v3 squared. And I'm going to multiply that by 2 to isolate v3. And then take the square root. And I get an answer of 23 meters per second is the velocity at point 3. Which again, we expected it to be less than at point 2 because some of our energy at point 3 is in gravitational potential energy. And finally, we can do the same steps for step 4, part C. We can use the same energy that we started with at position 1 and set it equal to the position 4. And we can really, if we know the velocities, do the same thing for positions 2 or 3. And again, that's 490 times the mass. And at position 4, we have the GPE at 4 plus the kinetic energy at 4. It has height, so it has GPE, and it has speed. So we have KE. Plug in the values I know. That's going to be mg, the height at 4, plus 1/2 m, the velocity at 4 squared. Once again, the masses cancel. I plug in the values I know. 490 equals 9.8 times the height at 4, which is 16 meters, plus 1/2 v4 squared. Going to do a little bit of math to isolate v squared. 19.8 times 16 is 156.8. So I'm going to subtract that from 490. Going to multiply that answer times 2, and then take the square root of that answer, and I get a velocity of 25.8 for v4 meters per second. And again, that's a little bit more velocity than at point B because it's lower, and it's gained some energy and transferred to kinetic energy at that point. So I hope this example gives you an idea of how we're going to solve some problems. If you look at your web assignment that's due for Friday, you've got some very straightforward ones with work, force times distance. You see a crate moving horizontally. You see one being moved vertically. You see work done to catch a ball. A distance the glove moves. Make sure we're in meters, but you have a force and a distance. They're asking for kinetic energy in number 4, and they give you a mass and a velocity. We have an equation. It's another kinetic energy for number 5. Make sure, again, we're in kilograms for everything. Number 6, we're calculating work. Again, gravity can do negative work to move an object in the wrong direction. So keep that in mind in number 6. You got sliding down a frictionless hill with some height. You get a transfer GPE to KE. Another ball moving a glove backwards, very similar to what we've seen. And number 9 is probably the closest to what we just did, except now it's an athlete jumping over a bar. So hopefully you have the tools now with our conservation of energy and our GPE and KE equations to be able to solve all your WebAssign problems. If you have any questions, shoot me an email and enjoy your days off. Thanks.